For most of medical history, if you wanted to see inside the human body, you had one option. You had to cut it open. But then, in the 1970s, this revolutionary technology came along and changed literally everything, giving us an incredible new window into our own biology.
So how do you do it? How do you see inside a living, breathing person without making a single incision? I mean, think about it. That question drove medical innovation for over a century, and it led us directly to the incredible technology we're going to break down today, the computed tomography scan, or, as you probably know it, the CT scan.
Okay, to really get why this was such a game changer, you have to think about a standard X-ray first. It's basically a shadow puppet on a wall, a flat, 2D image where all your internal parts are just piled on top of each other. A CT scan, on the other hand, gets rid of that overlap completely. It gives doctors a detailed 3D cross-section. It's the difference between seeing a jumbled shadow and holding a perfect little model in your hands.
All right, so here's our game plan. We're going to kick things off with the flat image problem, then get into exactly how CT scans work. After that, we'll check out what doctors can see and some really unexpected uses. And finally, we've got to tackle the serious stuff, the radiation question and the dose versus quality dilemma. Let's jump in.
So, first up, the flat image problem. This is all about why a simple X-ray, as useful as it is, just doesn't always cut it. So the big problem here has a fancy name, superimposition. But all it really means is that a standard X-ray squishes everything down into one flat image. Think about it like this. Imagine trying to find a problem inside a complicated building just by looking at its shadow. You can see the basic shape, sure, but you have no idea what's in front or what's behind. You know, is that little dark spot a tumor deep in the lung, or is it just the shadow of a rib in the way? That was the exact puzzle doctors were trying to solve every single day.
Okay, so if that flat shadow just isn't good enough, how in the world do you build a 3D picture? Well, that brings us right to our next section, how these things actually work.
You know, the name itself gives us a massive clue, computed tomography. It actually comes from two Greek words, tome, which means slice, and graphein, which means to write. So a CT scan is literally writing with slices. And honestly, that perfectly sums up the whole idea.
So how does it write with these slices? Okay, picture this. You're lying perfectly still, and an X-ray tube and a whole ring of detectors start spinning around you, like super fast. It's this high-tech ballet, and it's taking hundreds of measurements from every possible angle. Then a powerful computer takes that absolute flood of data and, using some seriously complex math, it reconstructs it all, slice by digital slice. And what you get at the end is one of those incredibly detailed cross-sections, a perfect virtual slice of your body.
All right, so we have these amazing digital slices. What does that actually mean for a doctor? What's the real-world payoff? Well, that's what Section 3 is all about, what doctors can actually see with this incredible power.
And honestly, the applications are just astounding. With a CT scan, a doctor can look right inside the brain to spot a stroke, a tumor, or a bleed. They can see tiny changes in the lungs that are completely invisible on a regular X-ray. In the heart, they can find calcium deposits that signal coronary artery disease. And in the abdomen, they can pinpoint kidney stones, assess inflammatory conditions like Crohn's disease, or stage the extent of cancer. It even provides a crystal clear view of complex bone fractures. This tool gives them a level of detail that was once pure science fiction.
But here's where the story takes a really cool, unexpected turn. This technology is so powerful, it's actually escaped the hospital. So welcome to Section 4, Unexpected Uses, because it turns out CT scans are definitely not just for medicine.
Okay, this is where it gets really wild. Paleontologists are using CT scanners to see inside delicate fossils without ever having to crack them open. Historians are virtually unwrapping ancient Egyptian mummies and scrolls to read things that have been hidden for thousands of years. The scanner that checks your luggage at the airport for threats, yep, that's CT technology. And manufacturers use it to inspect engine parts for tiny flaws you could never see with the naked eye. It's the exact same idea, writing with slices, just used on a whole different universe of stuff.
Okay, now, we can't talk about all this amazing power without talking about the other side of the coin. And that brings us to Section 5, the radiation question. It's really important we understand the dose that comes with these scans.
So to really get a handle on the dose, you need some context. A single chest X-ray, for example, is a tiny, tiny dose, about 0.02 millisieverts. Now compare that to what you get just by living on planet Earth.
That's about 2.4 millisieverts a year, just from natural background radiation. A head CT is kind of in that same ballpark, but a chest or an abdominal CT, we're talking way more. It's like getting several years' worth of that natural background radiation all in one go.
So what does that actually mean for your health? Well, it all boils down to probability. The best estimates suggest that a single abdominal CT scan adds about a 1 in 2,000 chance to your lifetime risk of developing cancer. Now, that's a small number for sure, but it's not zero, and that's exactly why doctors have to weigh the options so carefully, every single time, to make sure the benefit of getting that clear picture is absolutely worth the risk.
And this constant balancing act, this weighing of risk versus reward, leads us straight to our final section, the dose versus quality dilemma. This is pretty much the central challenge in medical imaging today.
So here's the fundamental trade-off that radiologists deal with on every single scan. If you use a higher radiation dose, you get a clearer, sharper, higher resolution image. But if you lower the dose, the image starts to get noisier, kind of grainy like a bad photo. And that noise could actually hide the tiny little detail the doctor's looking for. So the real art and science of it is finding that perfect sweet spot, using just enough radiation to get a clear diagnosis, but absolutely no more than necessary.
And you should know, the medical community takes this dilemma extremely seriously. It's led to these huge safety campaigns, like Image Gently, which is all about lowering the dose for kids, since they're more sensitive to radiation, and for adults, there's a campaign called Image Wisely. The goal for both is exactly the same. Use the absolute lowest dose you can while still getting an image that's good enough to make a diagnosis. It's all about being both incredibly powerful and incredibly responsible. So, here we are, full circle. The CT scan is, without a doubt, a life-saving, incredible window into the human body. But with that kind of power comes a whole lot of responsibility. And it leaves us with one last, really important question to think about. We've built this amazing window, but how do we decide, as patients, as doctors, when it's really, truly worth looking through?